All right, I'm very happy to be here again at the Triton conference to present Proton. In the last year, we have developed a lot of features integrating into Proton upstream, and I just cannot wait to share them with you. Here's a brief outline for today's 30 minutes talk. At the beginning, we are going to go briefly with Proton's overview of its features and its purpose. In the next, I'm going to introduce the major APIs and use cases that use these APIs for performance analysis. Next, Yuanwei is going to introduce you one of the major features we have integrated upstream, which is intra-kernel profiling. Next, Keren has a demo that shows you how to use intra-kernel profiling to analyze real-world kernels. I'm going to conclude the talk with our roadmap and a QA session. So as you know, Proton is the default profiler for Triton that provides a quick, simple, and intuitive way to inspect kernel performance. It's fully open source. All the code exists in Triton upstream. It already supports multiple vendor GPUs, including AMD and NVIDIA GPUs. I believe Intel backend also has its own Proton profiler. There are two outstanding features of Proton comparing to other vendor-provided profilers. The first is that it can annotate scopes on both the host side and the device side and aggregate metrics. The second is that we can collect metrics from both the hardware and the software. In the next two slides, I'm going to show you two profiling outputs of Proton, including the call path profiling view and the timeline tracing view. Let's start with the call path profiling view. So here, what you can see is a nested tree-like structure with multiple levels, all the way from the root of the program execution to individual kernels and lines within this kernel. There are two columns here in this view. The first column shows the number of instruction samples that we collect on the GPU. The second is the time spent in GPU kernels. Each level has metrics aggregated from itself and the children down below. Moving downward to the second last level, we have a customized kernel name with its original name, the grid size, cluster size, the other parameters like shared memory usage and number of stages. Then in the last level, we have number of samples aggregated at individual lines with its file path, function name, and line number. Instead of using the profile view to show you the overall performance of your program execution, we have also developed the timeline tracing view and supports both Chrome trace and Bravado. So comparing to the profile view, the timeline trace view is going to show you more detailed information, like the start and end time of each kernel on GPU streams. Here, this example only has one GPU stream, so you only see a single line. If you move a pointer and click one of the color regions here, you can see the detailed kernel info, like the name of the kernel and the duration of the kernel on the bottom left side. On the right side, we have the call path to this kernel. Here's Proton's overall architecture. It accepts profiling options from both the command line as well as the Python interface. The profiling options are passed through the front end to the back end. The back end is going to initialize profiling sessions that consist of the context, the backend profiler, the data. So we can use different profilers, vendor-provided APIs using our unified profiling interface that supports CUPTI, Rock Tracer, as well as our own instrumentation backend. When the profiling session is finalized, we're going to dump the data into both the trees view as well as the tree-like view, as you have seen before. All right, next we are going to get into the major APIs and one of the use cases. As I mentioned, Proton supports both the command line-based interface and Python API-based interface. The difference is that using command line, we're going to just provide all the kernels. But using Python APIs, we can provide more fine-grained control over what kernels and what regions we want to profile. For example, you can start a profiling session, and if there are code that you are not interested, you can skip the session based on the deactivate API and reactivate it upon the interesting region again. Proton supports, as I mentioned, 3 backends to date. The major API we're going to use to start profiling is called proton.start. That consists of 3 arguments, including the profile name, which you can use it to find a profile on the disk, the backend, and the mode. tied to the specific backend. On NVIDIA GPUs, we can use CUPT for both the timing and instruction sampling mode. On AMD GPUs, we currently support the timing mode. On both AMD and NVIDIA GPUs, we can use the instrumentation backend for the intra-kernel profiling mode. Next, I'm going to introduce the scope annotation and metric selection, as well as the hook-based annotation and metric selection. We define scope as a user-defined region with semantic information. For example, you can define and group your modules like MLP, or you can define the execution phases like the forward phase or the initialization phase or the backward phase. Scopes can be associated with user-defined metrics such as number of flop operations, number of bytes, and number of tokens. Sometimes using scopes, you need to extensively modify your user code. If you don't like it and just want to inspect the performance of kernels, we also provide a way to use a more clean way to inspect kernels with customized metrics, which is hooks. Hooks are those callbacks that launched before and after Triton kernel launches. Using hooks, basically you need to define callback with 3 arguments, including the grid size, the metadata, as well as arguments associated with the kernel launch. Then, performing some user-defined metric calculation, we're going to return a dictionary consists of the name of the metric as well as the value of the metric. Here's a more concrete use case of Proton when we are going to use it for the persistent matmul case. So it's designed for matrix multiplication with a small k dimension. We can use multiple algorithm variants. We can either use the persistent version or non-persistent version. We can use TMA or non-TMA. We can create the tensor descriptor on the host or on the device. We can try to enable warp specialization or write the algorithm without it. This complex choice of algorithm variants imposes challenges to the profiler and requires it to provide features such as providing rapid feedback on the hardware utilization, like the peak flops utilization comparing to the hardware limitation, as well as the memory bandwidth or the roofline utilization rate. In addition, we want to compare the performance introduced by different algorithm variants, and we want to compare our own implementation with hardware-based libraries such as cuBLAS and RockBLAS to use them as baselines. Then we're going to use the scope API we introduced before to annotate these information, including the matrix shapes, as well as the phase that this kernel is running, because during the auto-tuning phase, we could generate a large number of kernels, but sometimes we want to differentiate with the finalized kernel that is actually running. Besides, we want to differentiate the Triton-based kernels with cuBLAS kernels and Torch-based kernels. We also define hooks to inspect information such as the grid size associated with this kernel launch, as well as the number of warps, number of stages, and algorithm variants related with this kernel. All this code has already been integrated into the Triton tutorial. You can find this example in 09 persistent matmul.py and run it on your laptop or server. So here's the output of the persistent matmul tutorial on the command line. So you can see it has information about the flops of different algorithm variants, as well as cuBLAS and Triton-based implementation. We're running this example using m equals 8192, m equals n, as well as k equals 512. Under this configuration, we can see the best performance were achieved by cuBLAS and Torch kernels. They basically use the same implementation. And Triton kernels, our own customer implementation, is a little bit behind it. But this is running under flop 16. I believe if you run it using flop 8, then our implementation is a bit faster than cuBLAS kernel. Then I will hand the control to Yuanwei and let him introduce you the intra-kernel tracing and profiling functionality.
Thank you, Keren. Okay, so at Meta, we have seen an increasing trend in production use cases. Users demand more control and performance from Triton. As a result, there is a desire to understand more about the kernel behavior. And you know, GPU hardware is becoming increasingly complicated. And there is a recent shift to a producer-consumer type data flow programming model. So, for example, during kernel optimization, without knowing the critical path, you probably will rely on guess and check. For example, you change a little piece of your program and test its performance and hope you have a performance gain. The sampling-based profiling tools like NCU and Rock Tracer cannot really help you here. So we introduce the intra-kernel profiler, which gives you the capability, allow you to use flexible user-defined fine-grained profiling on timeline scopes and OP-level latency. It is compiler integrated, which means you have the full Triton stack support. And more interestingly, it unlocks and enables you to do a customized analysis and optimization. For detailed discussion, please see our K-perf-IR paper at this year's OSDI for detailed discussion. So what does it mean to you? How can this tool help you? First, you can leverage the timeline trace view to help you to identify the critical paths. Here, for example, the red lines are the critical paths of this attention-like kernel. Second, you can use it to detect resource contention. For example, you want to overlap or interleave the execution between CUDA core and SFU, like the red boxes and the black boxes here, to improve the hardware utilization. Also, you can use it to measure operator latency. For those critical operator latency, you can get a hint about how you partition your kernel and schedule the computation in your kernel. If you are willing to post-process the trace, you can even check the load balancing issues in your kernel and observe the scheduling behavior, the thread block scheduler behavior. Or you can see the wave quantization issue, like by comparing the occupancy across time and the SMID. Or even more, because you have access to the compiler IR, you can even customize the trace processing to visualize the software pipelining, like the behavior, and to check whether you squeeze out those bubbles. For example, here, number of stage, the difference between number of stages equals 2 and 3 is basically the overlapping of the load operation across iterations. Also, it's also possible to get some statistical traces about asynchronous operator latency across iterations and across its distribution. So how do we design this? We have two requirements. The first is we want to keep the Proton IRs independent from Triton IRs for isolation and maintenance purposes. Second, we want it to be compatible with Triton's existing IR model and execution model. So we introduced two dialects, which is Proton dialect and the Proton GPU dialect. The figure shows how it fits into the entire Triton compiler ecosystem. Proton IR basically is the front-end annotation. And the Proton GPU IR can be summarized as three categories: the operators like resource allocation and the runtime related and the finalization. During the runtime, we automatically allocate resources like global memory and the shared memory. And each thread block has a profiling buffer, which is organized into warp level segments. And each segment is organized as a circular buffer. So the number of events can be different in each segment when you profile a warp specialized program. Keren has just mentioned about the profiler APIs. So for the intra-kernel profiler, the host side APIs are marked in red. And you can see here, if you want to pick which mode, like is it you want to measure operator latency, or you want to visualize the timeline trace. You just need to tweak the data field in the API. We've also recorded a demo to show you these cases. You will see them in a minute. On the device side, for now, we have two approaches. First approach is using the Proton DSL, which you can basically annotate to your kernel using the Proton operators. We support Trident, Gluon, and the TLX. For Trident, it's a little bit tricky because Trident performs heavy optimization, loop-level optimizations. It might distort your annotations. So instead, we recommend you to use the second approach, the IR override approach, which basically you annotate your kernel at the TTGR level using the Proton operator. It is the most general and the DSL agnostic approach for intra-kernel profiling. Next, we will see some live demo. My colleague Corbin will give you a short description about the use cases.
We'll start off with the basic Triton vector add tutorial example. We explicitly enable Python DSL level annotations using the PL enable semantics line here. We can then insert nested Proton scope timing statements directly into the Triton kernel. Here we have load and add, load X issue, load Y issue, and then the outer level kernel scope. Running this now instrumented kernel outputs a Chrome trace file with the intra-kernel timings. We can also dump the IR files and inspect the TTGIR to see the Proton record ops added. We can see those here and here. We note that because we are instrumenting at the DSL level, we rely on the compiler to lower the Proton timing regions for us. One example is the X load issue region here includes more than just the TT load instruction. Opening the Chrome trace file in Perfetto shows the per CTA warp level profiling data. We explicitly set 8 warps per CTA in the kernel, so we see 8 distinct warp traces, each with nested scope labels. Mousing over each one of the nested labels, we can see the timing that each one takes.
The second example makes use of the more accurate intra-kernel profiling workflow of modifying and overriding the kernel's intermediate representation directly to insert profiling annotations in the code. Modifying the generated TTGIR files by adding the Proton record operator directly allows for more fine-grained control over the profiling regions, since we are not relying on the compiler to correctly lower the profiling ops from the DSL level. The kernel override-based workflow has 3 steps: generating the kernel's intermediate representation files, inserting profiling annotations in the TTGR files, and rerunning the modified kernel code with both the Proton code hooks and the kernel IR override options. We take the same vector add tutorial as before, however we start with the completely uninstrumented code. There are no Proton ops in the top level DSL. We run and modify the kernel's TTGIR and modify it directly either through a script or by hand. The X load issue region now from before, we are only including just the TT load instruction. As before, we had other instructions in between. We then run the kernel again with the kernel override environment variable set on the command line, along with the path to the kernel's new IR files set through the Triton override directory environment variable. Opening the Chrome trace file in Perfetto again, we see the nested scope labels and region timers, however this time with more fine-grained instruction resolution.
Okay, it's done. Oh, all right. Thanks, Corbin, for the recorded video. Okay, so we have seen that there are many interesting features in Proton, and it's been used in the production for a while. However, I still want to see that our work is not perfect, and we need to improve it further in the future. For example, in intra-kernel profiling mode, we do want to support more customized inspection code. And to date, we still, in the upstream Proton code, we still only support using SRAM to store shared memory to store profiling buffer. There are cases where the SRAM is limited and has already been used by the application. In such cases, we want to extend profiling buffer to DRAM for more robust profiling. In addition, you can see that now that we can show all these tiny regions on the trace line, but for multiple kernels and cases where these color regions are sparse, it's kind of hard to tell where these regions exist. So we want to improve the visualizer to support profiling for multiple kernels to develop a more clean boundaries between these regions. We also want to improve the Fender API support. For example, we are using the legacy Rocktracer API to support profiling on AMD GPUs. We want to refactor all the software stack to support their own, their newest Rock Profiler SDK and support their PC sampling. In addition, we are also interested in profiling interconnect, basically the multi-GPU kernels. Also, we want to support more flexible and adaptive metric collection. To date, Proton does support profiling graph launcher kernels, like these kernels launched by CUDA-Graph. But the limitation is that we cannot associate custom metrics associated with graph launcher kernels. In addition, we want to refactor the metric derivation engine so that users can directly specify the derivation formula from the command line to derive their own metrics for analysis. In the end, we've realized that providing a simple command line output isn't perfect for many use cases, so we probably want to improve by making it an interactive command line visualizer. Okay, so this ends up the Proton talk. Happy to take any questions.
Hi. We haven't really used Proton very much, but we were investigating its use. And so one of the things that we specifically are looking at is when Triton lowers our code, as we change our kernel, Triton can lower the code in ways that are surprising. And so, it's very nice that there's kind of an intra-kernel API that you can time things, but considering your integration with the compiler IR, is it possible to kind of look at a load and be like, oh, this load was say vectorized, right? This is how many transactions are created from it or something like that, and then pull it out. So it's kind of like a combination. So normal, as far as I can tell, right, you can say that oh, this kernel has these metrics. You can say that this is how many bytes that I think it should use, right?
Yes.
Is it possible to kind of in an automated fashion also, for example, say oh, this kernel, you can look at the IR and be like, oh, this is how many bytes actually got loaded by the kernel or something like that. Is that something that you could do in Proton?
So first of all, we currently don't have such feature support. And I want to clarify about custom metrics collection a little bit. What we want to collect is the theoretical number of bytes or flops that will be performed by this kernel. It's somehow a little bit different from hardware-based collection, which collects all the DRAM bits and all the flops running on hardware components. There should be ways to figure it out by looking at the IR, but that is really kind of risky because you need to model the execution of this IR to know the dynamic variables like the number of loop iterations and simulate that workload to figure out what's the theoretical number.
Well, so the hope I had was that you do have an in-kernel profiler, right? As the kernel was running, we could collect these kinds of metrics and pull them out, right? Is that do you kind of understand what I mean?
Yeah, I got what I'm saying. However, I think it's still related with hardware-based behavior, right? Oh, so you are saying that we first run the kernel and then dump the metrics to somewhat kind of buffer.
Right.
Yeah, I think it's kind of doable.
Okay, cool.
Okay. Any other questions? That's it? Oh, sorry.
Yeah, so a couple couple questions. So, like the first part you mentioned was, is there some part common with the PyTorch profiler where you are correlating the host and the device? Is that functionality common with the PyTorch profiler?
So your question is there any relationship with our profiler and PyTorch profiler?
Yes, especially the part where you mentioned correlating the host and the device.
I don't think so. Yeah.
Okay, it's completely kernel level.
Right, it's orthogonal.
Okay. And yeah, just how invasive is this profiling? Like when you disable the profiling, how much does the performance differ?
Wait, so you're asking when I disable the profiling, how much overhead there is?
Exactly. Yeah.
There shouldn't be any overhead, right? Because profiling is disabled.
No. When compared to when you enable the profiler.
Oh, okay, yeah. So
invasive.
it depends on which mode you're running on. Do you want to, if you want to run the coarse grain profiling, only profile the kernel performance, then it can depend on the hardware provider's API, profiling API, how much overhead it imposes. Usually it's just less than 10 or 20%. If you use the intra-kernel profiling mode, then it kind of depends on what SRAM has already been occupied by the kernel. Usually it's, for memory-bound kernels, it's usually less than 10%, I would say. We have seen one outlier on AMD's field extension kernel, where we have triggered something like 50% overhead, but it could be mitigated by further improvements, like moving the data from SRAM to DRAM.
Thank you.
Thank you.
Right, sorry, I had a question. Could you possibly use MLIR location data to avoid having to manually add in, like in the TCG-IR, the like start and end, or is MLIR location too like coarse-grained to add those like finer grain like start and end?
Sorry, I don't get how we can achieve that. Are you saying that we automatically generate like start and end scopes?
No, I'm saying is that like, is it kind of like, what are the limitations of not using the TTGIR? So if I didn't want to manually edit TTGIR and add it in, like, is there a better way to like add those start and end?
So first, if you are writing a Triton kernel and want to inspect its performance, in theory, you could do it at DSL level. It's just sometimes it's not precise and may break your kernel if you instrument within the loop. If you use Gruen to write your kernel, then it's the same to use DSL API as using the TTGIR-based instrumentation.
Okay, I think it's, yeah.
Yeah, thank you. Okay, thank you all for attending the morning session.
Thank you very much, Keren and Yuanwei.